This is the video lecture for CHY 40, Unit 2, Chemical Bonding, Part 2, Bonding Theories and Molecular Geometry. Theories of covalent bonding. First is valence band theory. So it tries to explain the bonding process, the merging of valence atomic orbitals to form an overlap region. The overlap region can only accommodate maximum of two electrons of opposite spins to form a covalent band. So for example, for H2, there are two hydrogen atoms, and when they bond together, there is an overlap region, and this overlap region can accommodate a maximum of two electrons of opposite spins to form a covalent band. So another example is HCl. So we know that hydrogen is 1s and chlorine is ang iyahang valence electron is at 3p orbital. So um, para mag-bond sila, there is a overlap region, and this region can accommodate maximum of two electrons of opposite spins. And then this overlap region will form a covalent bond. Same with Cl2. Next is hybridization. So it is the process of mixing of atomic orbitals of the same atom to form degenerate orbitals or orbitals of the same energy called hybrid orbital. The number of hybrid orbitals formed is equal to the number of pure atomic orbitals that combine. So first is the sp hybrid orbitals. This is the mixing of one s and 1p orbital. So, inani iyahang picture. So, a 1s orbital and a 1p atomic orbital. So, as you can see, as I have discussed, ang nawong sa p orbital is like a dumbbell. So, when they are bonded together or mixed together, inani na ang picture. So, when they are shown together, ang large lobes lang ang makita. So, example is BeCl2. So, the ground state orbital diagram for beryllium is looks like this. So, for na-fill niya ang 1s orbital, so 1s2, and then iyahang 2s orbital. But this indicates that beryllium does not form covalent bonds with chlorine since beryllium's electrons are already paired at 2s orbital. So to be able to form two bonds, one of beryllium electrons must be promoted to 2p. Now, there are two beryllium electrons for bonding, but this indicates that the two BeCl bonds are different since one forms from a 2s orbital and other from the 2p orbital. But experiments indicate that the two BeCl bonds are equivalent because the 2s and 2p orbital hybridizes to form two equivalent sp hybrid orbitals. So naa na dayon si beryllium two bonding electrons para maka-form siya og BeCl2. Next is for sp2 hybrid orbital. So this is the mixing of 1s and 2p orbital. So inani iyahang picture. When they are shown together, inani siya. Only the large lobes can be seen. So example for sp2 is Bf3. So the ground state of orbital diagram for boron is looks like this. So nanay isa ka electron sa 2p orbital. And promoting one of Bs or boron's 2s electrons to 2p. So now there are three boron orbitals for bonding. But this indicates that two of the Bf bonds from 2p should be the same, but one from 2s should be different. But experiments indicate that the three Bf bonds are equivalent because the 2s and the 2p orbital hybridizes to form three equivalent sp2 hybrid orbitals. Therefore, naa na siya three bonding electrons nga pwede makaband og tulo ka fluorine. So, naa-din tay compound nga BF3 or molecule nga BF3. So for sp3 hybrid orbitals, it is the mixing of 1s and 3p orbitals. So it looks like this. And when shown together, inaniiyaha nga nawong, but then ang large lobes lang ang makita. So example is CH4. So we know that the valence electron of carbon is 4. So when the um, one of the electron in the 2s orbital can be promoted to the empty orbital of 2p. Therefore, naanay 4 bonding electrons ang carbon. So when this is hybridized, it is mahimo siyang sp3. So another is sp3d hybrid orbitals. It is the mixing of 1s orbital, 3p orbitals, and 1d orbital. For sp3d2 hybrid orbital na ay magmix ang isa ka s orbital, 3p orbitals, and 2d orbitals. So as a summary, naadiri sa table, naadiri ang hybrid orbitals, then their geometry and examples. So guidelines in predicting the hybrid orbitals form. So first, draw Lewis structure to determine total number of bonds on central atom. Then given the Lewis structure, we can determine what hybrid orbitals must be involved by counting the number of bonds around each atom. So counting multiple bonds as one number of and number of lone pairs. So example for SF6, so count i-count daw ang number of bonds which is 1, 2, 3, 4, 5, 6. Kung 6 iyang number of bonds, na siya sp3d2. So let's check. SF6 is sp3d2. Another example, NH3. So let's count 1, 2, 3 plus 1 lone pair or 2 lone pairs. So 1, 2, 3, 4. So 4 is sp3. Let's check. NH3, sp3. So inana lang pag predict sa hybrid orbitals. Okay, theories of covalent bonding. Number 3 is the valence shell electron pair repulsion theory, or the VSEPR theory. So the best arrangement of a given number of electron pairs is the one that minimizes the repulsion among them. The valence electron pairs, or electron domains surrounding an atom, repels one another, so the orbitals containing those electrons are oriented as far apart as possible. So these are the types of valence electron pairs: the bonding pairs, which are the shared electrons, and the non-bonding pairs, which are the lone pairs. And types of electron repulsion. So the lone pair repulsion, lone pair bonding pair repulsion, and bonding pair repulsion. And the degree of repulsion, so makita ninyo diri na ang pinaka less og degree of repulsion is the bonding pair repulsion. Og ang pinaka dako og degree of repulsion is lone pair. Electron domain. It is a region in which the electrons will most likely be found. So for lone pairs or the non-bonding electrons, these are the electron domain located principally on one atom. So for the bond pair, these are the shared among bonded atoms. For the molecules which has no lone pair, so inani iyahang general formula. A, B, Z, subscript Z, where A is the central atom, and B is the outer atom, and Z is from 2 to 6 outer atoms. Okay? So first, AB2. So, naay duha ka outer atom. So, ang iyang geometry is linear. Again, this is for the walay lone pairs. So, for AB2, iyang geometry is linear. The two outer atoms, ang duha daw ka outer atoms, are 180 degrees from each other. So, example is HCN. So, inani iyahang nawong. So, ang H and N na siya 180 degrees nga angle, therefore it is linear. So for AB3 or nanay tulo ka outer atoms, yung geometry is trigonal planar. So three outer atoms at the center of an equilateral triangle. Each outer atom is 120 degrees from the other two outer atoms. So example is CH2O. So inani ang structure ni CH2O or formaldehyde. Then, ang angle daw niya from the corners, from the atom to another, or from the outer atom to the other outer atom is 120 degrees. So, for linear, 180. For trigonal planar, or naa siya AB3 nga formula, is 120 degrees angle. And another is AB4. So, nana siya upat ka outer atom. So, ang tawag sa iyang geometry is tetrahedral. So, maximum distance between electrons requires 3D structure with each outer atom to be 109.5 from the other outer atoms. So, inani gid ang picture. So dili lang siya flat. Di siya flat nga in plane lang siya, but inani iya nga actual nga figure for tetrahedral. So every angle from one outer atom to another outer atom, 109.5 degrees iyahang angle. For AB5, yung geometry is trigonal bipyramidal or bipyramidal or bipyramidal. So, the trigonal means there are three outer atoms form planar triangle around the central atom, and the bipyramidal, there are two outer atoms directly above and below central atom. Connecting outer atom forms two three-sided pyramids. So, inani iyahang for the positions, axial positions above and below central atom. So taas ug ubos, two atoms are at axial position or 90 degrees from equatorial atoms. And for equatorial positions, ends of planar triangle, three of the outer atoms are at equatorial position which has a 120 degrees from each other. So inani iyang picture. So this is the axial na naa siya 90 degrees from the equatorial, and this is the equatorial position which has a 120, so 120 degrees iyang angle from iyahang ka-equatorial nga position. So inani iyang picture, dili lang pud na siya flat or in plane ha. So inani iyahang nawong gyud sa trigonal bipyramidal. So kung naa kay lima ka outer atoms, inani iyahang geometry. Tawag sa iya trigonal bipyramidal. Okay, next. AB6 na kay 6 ka outer atoms, ang tawag sa iyang geometry is octahedral. So from the word itself, octa, naa siya 8 ka 8 or 8 sides. So connecting 6 atoms or 8 faces. All atoms are 90 degrees away from each other, and the terms axial and equatorial do not apply because all 6 positions are identical. So, nani ang picture. So, di daw siya matawag na ay matawag nga equatorial o axial tungod tanan angle is 90 degrees. So, inani ang picture. Nani gud iyahang geometry in actual nga molecule. So that is for octahedral. Naa siya 6 ka outer atoms. So in summary, for linear, 180 degrees. For trigonal planar, nga naa siya 3 ka outer atoms, 120 degrees. Tetrahedral na ay 4 ka outer atoms, tag 109.5 yang angle. For trigonal bipyramidal na ay 5 ka outer atom, So naay equatorial and the axial. So ang axial from the equatorial is 90 degrees, but for the equatorial and another equatorial, siya 100 degree nga angle. But for octahedral, so naay 6 ka outer atom, all angles is 90 degrees. So next is for the molecules where the central atom has one or more lone pairs. So yung general formula is A, B, Z, E, N, where A is the central atom, B is the outer atoms, and Z is from 2 to 6. So parehas sa ganiha nga outer atoms, but E is the lone pair, where and N is from 1 to 2 and the many more above. So first is AB2E. So naay duha ka outer atom and naay isa ka lone pair. So ang tawag sa iya is bent. So start with AB3 molecule or ang trigonal planar and replace a B atom with lone pair. The bond angle is now less than 120 degrees. So ang example is, so this is a trigonal planar. Atong example is CH2O ganiha. Og naa siya angle nga 120 degrees for trigonal planar. But when naa na siya lone pair, imuha dong pulihan ang isa kabi og lone pair, ang iyahang angle is now less than 120 degrees, ni 119 na siya because of the repulsion of the lone pair. Next is for the 4 electron domains, is first is the trigonal pyramidal. So naa siya tulo ka outer atoms and isa ka buok nga lone pair. So the central atom plus 3 outer atoms make a pyramid. So start with AB4 or tetrahedral and replace a B atom with lone pair. The bond angles are now less than 109.5 degrees. Example is NH3. So, mao ni di ba atong example ganiha sa tetrahedral, which is CH4, na siya bond or na siya angle nga 109.5 degrees. But pag abot sa trigonal pyramidal, molestan siya sa 109.5 because of the presence of one lone pair. So, ang pag-write ani is same sa tetrahedral, but then ilisan nimo ang isa og isa ka B or isa ka outer atom with one lone pair. Okay, so for the actual picture or actual molecule or geometry, inani iyang nawong. So this is the tetrahedral. Wait lang, di makita. This is the tetrahedral and this is the trigonal pyramidal. So makita ninyo ang naa sa taas na ilisan og lone pair. Okay, so and then ang iyang angle mas less na siya compare sa tetrahedral because of the repulsion of the lone pair. Next is the AB2E2 or iyang geometry is bent. So meaning na ay duha ka outer atoms and na ay duha ka lone pair. So start with AB4 or the tetrahedral and replace 2B from the AB4 atoms with 2 lone pairs. So the bond angles are now less than 109.5. So this is the tetrahedral again, but for the bent shape of AB2E2, example is H2O. So inani na iyahang picture. And from 109.5, mas less na siya. So nahimo na siya 104.5. So for the actual picture, nani na iyahang nawong. So, okay, nakuhaan og duha for the tetrahedral na pulihan og lone pair. Og ang iyahang angle ani is less than 109.5. For 5, ganiha for electron domains man to now is 5. So there are for AB4E na upat ka outer electron and na isa ka lone pair. So ang tawag sa iya is CISO or iyang geometry is CISO. So start with AB5 molecule and replace one X atom or one B atom with one lone pair. The B atom can be taken from an axial or an equatorial position. So the axial position, the lone pair is 90 degrees from 3 equatorial B atoms. So ang equatorial position, the lone pair is 90 degrees from 2 axial and 120 degrees from 2 other equatorial B atoms. Taking B atom from equatorial position is preferred since it maximizes spin between lone pairs and B atom. So, imong ibutang ang lone pair, mas preferred nga ibutang siya sa equatorial position. So, the bond angles are now less than 90 degrees and less than 120 degrees. Example is SF4. So, inani so this is the picture of the, ano siya, AB5. So, AB5 is trigonal bipyramidal. So, atong example ganiha is PCl5. But for CISO, so naa siya 5 electron domains, upat ka outer atom and isa ka lone pair. Example nato is SF4. So, makuhaan og isa ka B or outer atom pulihan og isa ka lone pair. So, for the actual picture, inani iya nga no. Okay? So, as ang giingon ganiha, mas preferred nga sa equatorial siya pulihan or kuaan compare dira sa axial. So, gitawag siyag siso maybe because wala siyag siso. Next is AB3E2, still 5 electron domains, but only 3 outer atoms and 2 lone pairs. So, ang tawag sa iyang geometry is T-shape. So, start with AB5, so trigonal bipyramidal, and replace 2 B atoms with 2 lone pairs. Both B atoms are taken from equatorial position to maximize distance between the lone pairs. The bond angles for remaining atoms are now less than 90 degrees. So, example is ClF3. Okay? So again, naapod siya dito siya gikuha, mas preferred nga dito ibutang ang lone pair sa equatorial than the axial. So mura siya T-shape ang gitawag sa iya because mura siya og T. Kung mura siya T. Okay? So ang iyang angle is less than 90 degrees. So, for 5 electrons, but tulo na imuhang lone pair and duha na lang imuhang outer atom. So start with AB5 molecule, which is the trigonal bipyramidal, and replace 3 B atoms with 3 lone pairs. The first 2 B atoms are taken from equatorial position, but the third B atom can be taken either equatorial or axial positions. So from axial, kung axial nimo ibutang ang lone pair, the third lone pair would be 90 degrees from other lone pairs, and kung equatorial, the third lone pair would be approximately 120 degrees from other lone pairs. Taking third B atom from equatorial position is therefore preferred. So mas preferred gyapon nga sa equatorial ang position nimo ibutang ang ikatulo nga lone pair to maximize space, and the bond angle is 180 degrees. So moong gitawag siya nga linear. Though naa siya tulo ka lone pairs and duha ka outer atom, ang iyang geometry is linear. Kay iyang angle is 180 degrees. So example is XEF2. So iyan na wong actual nga picture is like this. Mara na siya linear na siya. But there are 3 lone pairs in the equatorial position. Okay, for the 6 electron domains. So first is AB5E, meaning that na ay 5 ka outer atoms and isa ka lone pair. So square, ang geometry niya is square pyramidal. Central atom plus 5 B atoms make 4-phase pyramidal. pyramid, four-faced pyramid rather. So start with AB6 or the octahedral and replace one B atom with one lone pair. Since all 6 outer positions are identical, it doesn't matter which one you take. So remember that there are no axial or equatorial positions for octahedral. The band angles are now less than 90 degrees. Example is BRF5. So this is the octahedral. Kuhaan nimo og isa para imuhang pulihan og lone pair. So ang tawag na sa iya is square pyramidal. And the angle, the band angle, is now less than 90 degrees. So that is the actual picture for square pyramidal. Or siyag pyramid na. Ah. So next is still on the 6 electron domains but 2 lone pair and 4 outer atoms. So central atom plus 4 B atoms form square all in one plane. So start with octahedral and replace 2 B atoms with 2 lone pairs. Again, it doesn't matter which B atom is taken first, but the second B atom must be taken 180 degrees away from it to maximize space between lone pairs. The band angles are now exactly 90 degrees since lone pairs balance each other. So example is XeF4. So kung ipahigda nimo siya mura na siya square, mao ang tawag sa iya square planar. Okay? So remember that ang two lone pairs should be sa taas or sa ubos or 180 degrees band angle from the first lone pair then sa second lone pair. This table is the summary for the geometry, molecular geometry, and example um, for the molecules nga naay outer atom and naay lone pair. So, naaman ni siya sa inyong nga handouts. Electron pair or electron domain geometry. So it is the arrangement of electron pairs, whether lone pair or non or bonding pair, whether lone pair or bonding pairs around the central atom. The molecular geometry is the arrangement of the atoms in space, which may be predicted from the electron pair geometry. It is the actual shape of the molecule. Steps in determining the molecular geometry. So first, write down the Lewis structure, then count the total number of electron pairs, the lone pair plus the bond pair around the central atom. Note that double bonds and triple bonds counted as one electron pair. From this, determine the electron domain geometry. So example, 1, 2, 3. So trigonal planar for COCl2. So same siya atong CH2O nga trigonal planar. If the central atom does not have a lone pair, then the molecular geometry shape is the same as the electron domain geometry. In the presence of lone pairs in the central atom, substitute the lone pairs for bond pairs, imaginarily removing one bond per lone pair and making certain that they are as far apart as possible. After having been considered the position of the lone pairs, predict the shape of the molecule referred to the figure as follows. So, kaninga table, naapod ni siya sa handouts. Non-bonding electron pairs or the lone pairs and electrons in multiple bonds exert greater repulsive forces on adjacent electron pairs and thus they tend to compress the angles between bonding pairs. So ang mga lone pair and multiple bonds gahatag sila o ga-exert sila og greater repulsive forces. Mao nang ang mga angles mas mugamay siya compare sa walay lone pair o walay multiple bonds. So for example, for kanang walay lone pair or walay multiple bonds, iyang angle for tetrahedral is 109.5. But if naa na siya lone pair, mahimo na siya or less than 109.5 na siya, mahimo na siya 107 degrees. Rules on electronic repulsion. So first is the type of repulsion. So as mentioned ganiha, bond pair and bond pair is naa siya less nga degree of repulsion compared to the lone pair repulsion. A bonding pair of electrons is attracted by both nuclei of the bonded atoms. In contrast, a non-bonding pair is attracted primarily by only one nucleus. Because a non-bonding pair experiences less nuclear attraction, its electron domain is spread out more in space than the bonding pairs. So the HXH bond angle decreases from C to N to O. So example, ang iyahang giingon dira nga ang bonding pairs which is the electron of hydrogen and carbon, they are attracted to the both nuclei of the bonded atom. So ang this bond attracted siya to H and to carbon. But in contrast, ang non-bonding pair, which is the lone pair, they are attracted primarily to only one nucleus. Kung aha siya na-attach, so dito siya mas na-attract. So that is why mas dako siya og space, mas spread out siya in space than the bonding pair. So makita ninyo as kung modaghan as the lone pair increases, the bond angle decreases. So there is greater repulsion among lone pairs as the number of lone pairs in the central atom increases. This results to a decrease in bond angle. Next, the increasing size and lower electronegativity of the central atom permits the lone pairs to be drawn out farther, thus decreasing repulsion between bonding pairs. So in order, for example, for O, S, and selenium, decreasing ilahang electronic repulsion. So iingon as the size of the atom increases, so di ba ang trend sa size sa atom from top to bottom mag-increase siya. But ang iyang electronegativity mo decrease. So oxygen or H2O has greater bond a greater electronic repulsion than sulfur and selenium. So selenium has the less electronic repulsion. Next is the repulsions exerted by bonding pairs decreases as the electronegativity of the bonded atom increases. So katong ganiha central atom, but diri for the bonded atoms or the outer atoms. So iyang ingon the repulsion exerted by bonding pairs decreases as the electronegativity of the bonded atom increases. So, di ba, fluorine is the most electronegative element. So, kung mag-increase ang electronegativity sa bonded atom or sa outer atom, mas less ang iyahang repulsion. Next is the presence of multiple bonds increases repulsion between bonding pairs. So, kung mas daghan siya kung multiple bonds siya, mas dako iyahang repulsion or naay increase in repulsion compared to the single bond. Next, in trigonal bipyramidal double bonds, lone pairs, and less electronegative atoms preferred the equatorial positions. In octahedron, any lone pair occupies any position, and the result is always square pyramidal geometry. However, if the two lone pairs are present, they must be opposite to each other. So, mananing square planar geometry. Next, the multiple bonds do not affect the gross geometry of the molecule because the geometry is primarily determined by the number of sigma bonds and lone pairs. Lone pairs occupy hybrid orbitals while multiple bonds do not. Okay, we will go to the polarity of polyatomic molecules. A polar covalent bond is a consequence of the unequal sharing of electrons. It results from two bonded atoms with different electronegativities. Meanwhile, a nonpolar covalent bond is a result of the equal sharing of electrons between bonded atoms which have the same electronegativity. So as what we have discussed sa part 1, those are the polarity of covalent bond. But now, this is the polarity of molecules. So for a molecule with more than two atoms, the dipole moment depends on both the polarities of the individual atoms and the geometry of the molecule. Note that bond dipoles and dipole moments at vector quantities, that is, they have both a magnitude and direction. The net dipole moment of a polyatomic molecule is the sum of its bond dipoles. For example, in carbon dioxide, both CO band are polar, but the entire molecule is nonpolar. The two bonds in carbon dioxide or CO2, although equal in magnitude, are exactly in opposite direction. So makita ninyo. So this is the carbon and this is the oxygen. So ilahang though polar ang C and O nga bond, but ilahang dipole moment is opposite. So the bond dipoles cancel each other, resulting to a net dipole of 0. On the other hand, for water, the bond dipoles are also in equal magnitude. So ang O of H and O of H diri sa left side, na sila same nga magnitude sa ilahang bond dipoles. But then, the bond dipoles are also in equal magnitude but do not exactly oppose each other tungod sa ilang geometry. Diba? So thus, it has a non-zero overall dipole moment and is therefore polar. So ang geometry for CO2 or carbon dioxide is linear. So that is why mag-cancel sila. But for H2O, bent iyahang geometry and also ang iyahang net is or ang iyahang dipole is padulong sa oxygen because mas electronegative man ang oxygen than hydrogen. That is why dili sila mag-cancel and is therefore the H2O is polar. Molecules in which the central atom is symmetrically surrounded by identical atoms are nonpolar. So, for ABZ molecules in which all the B atoms are the same, certain symmetrical geometries like linear, trigonal planar, tetrahedral, and square planar, trigonal bipyramidal, and octahedral must lead to non-polar molecules even though the individual bonds might be polar. So kung same ang outer atoms, possible gyud nga non-polar ang molecule, bahalag ang individual bonds is polar. Next, the molecular orbital theory. So this describes the electrons in a molecule by using specific wave functions called molecular orbitals. Just as electrons in atoms are found in atomic orbitals, electrons in molecules are found in molecular orbitals. It has definite or discrete energy states. Ang molecular orbitals, it has definite or discrete energy states. The electron density distribution can be represented by contour diagram. So, similar sa atomic orbitals na apod siya S, P, D, and F. Molecular orbitals are formed by the linear combination of atomic orbitals, and the overlap results in the formation of sigma and pi bonds. Sigma bond. It is formed by the head-on overlap of atomic orbitals. The electron density is centered about an imaginary line passing through the nuclei. Sigma bonds are free to rotate about the axis, while pi bond, these are formed from the sideways overlap of atomic orbitals. It concentrates electron density on opposite sides of the line passing through the nuclei. The overlap region lies above and below the internuclear axis. A pi bond can be formed only if unhybridized p orbitals are present on the bonded atoms. It can introduce rigidity into the molecules or no free rotation. So for sigma bond, they are free to rotate, but for pi bonds, there is no free rotation. So for pi bonds, ganiha, um, head-on overlap ang sigma bonds, while for pi bonds, sideway overlap. So kani, this is the pi bond. Okay, mas klaro diri. So ang sigma bond overlap nga head-on, while ang pi bond is sideways overlap. So this is the internuclear axis. So sideway. So example is ethylene or C2H4. The CC bond has one sigma and one pi bond. Both carbons are sp2 hybridized and have trigonal planar electron pair and molecular geometry. So kung kanilang, this is um, trigonal planar yung geometry. So, same with this. So, makita ninyo ang CC bond na siya 1 pi bond and 1 sigma bond and 1 pi bond. So, ang overlap nila nga head-on, that is the sigma bond. But ang sideway nga overlap, that is the 1 pi bond. Another example is acetylene or C2H2. So each carbon is sp hybridized and thus have linear electron pair geometry. So this iyang geometry is linear. The sp hybrid orbitals form the CC and CH sigma bond. So ang CC naa siya isa ka sigma bond, ang CH naa pod siya isa ka sigma bond. So in total for C2H2 naa siya 3 sigma bonds. The two unhybridized kaning duha diri, the two unhybridized p orbitals form the pi bond. So as you can see in this picture, in this figure, ang overlap mo na ang sigma bond. So overlap with the CC bond, head-on overlap, I mean. The head-on overlap for CC bond is 1 sigma bond and the head-on overlap for C and H bond is 1 sigma bond. So same with the other. But for the CC bond, naapod siya pi bond. So the two unhybridized p orbitals form the pi bond. So kaning nasa taas o kaning sa ubos. Another example, so in the case of benzene, there are 6 CC sigma bonds formed from the overlap of 6 sp2 hybridized carbons, 6 CH sigma bonds, and 6 unhybridized p orbitals that lie perpendicular to the plane of the molecule. So, ang structure sa benzene is this, diba? So, you can see nga naay alternate nga double bond. So, every bond with C and C, ang 6 ka carbon, naa siya tag-isa ka sigma bond, na ay overlap, ay head-on overlap nila. So, same with the C and H. So, that is sigma bond, kay head-on overlap man. But then, the 6 unhybridized, so, kaning double bond, nga perpendicular to each other, produces pi bond. So, kanang naay double bonds, naa na siya pi bond. So, in total, for the benzene, naa siya 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 sigma bonds, but 1, 2, 3 pi bonds. So, iyahang resonance structure is this. So, inani iyahang picture na ay overlap with head-on overlap for this. So, mao nang naa siya 12 12 sigma bonds and 1, 2, 3 pi bonds. Bonding molecular orbital. So it concentrates electron density between two nuclei. It has lower energy and thus more stable. For anti-bonding molecular orbital, it is characterized by anodes, which are regions where atomic orbitals tend to cancel each other. So, ang bonding molecular orbital, it has lower energy. So, mas gamay siya energy compare sa anti-bonding, but it is more stable compared to the anti-bonding molecular orbital. So, for anti-bonding molecular na siya node, it is characterized by a node. So, ang node are the regions where atomic orbitals tend to cancel each other. Bonding electrons occupy the bonding molecular orbitals, while the anti-bonding electrons or the lone pairs or the anti-bonding electrons occupy anti-bonding molecular orbitals. So bond order is related to the stability of covalent bond. So the formula or to get the bond order, you have 1/2 of the bonding electrons minus the anti-bonding electrons. So if you have one bond order na kay isa ka sigma bond, so that is single bond. But kung duha mong bond order na kay isa ka sigma bond and isa ka pi bond, so meaning na kay double bond. So for kung tuloy mong bond order na kay isa ka bond, sigma bond and duha ka pi bond, so that is the triple bond. But kung wala kay or zero imong bond order, molecule does not exist. So for example, H2. So there are two hydrogen atoms, which is equal to 2 molecular orbitals. So for H2, in H atomic orbitals, we know na ay duha ka hydrogen. So na siya 1s, mag-combine siya with another 1s. So, hydrogen and another hydrogen. So, in constructive combination, it leads to the bonding H2 molecular orbital. So, this is the bonding molecular orbital. But for destructive combination, it leads to the anti-bonding H2 molecular orbital. So, as you can see, this is the nodal plane between the nuclei which cancels the atomic orbital or the atomic bonding. This figure is the molecular orbital for n is equal to 1. So, meaning, naa siya sa 1 energy level. So, inani iyaha nga nawong. So, for H2 molecule, this is the 1 hydrogen atom, mao ni iyang atomic orbital sa isa ka hydrogen. And for the other hydrogen, inani pod iyaha nga atomic orbital. So, both electrons in their atomic orbital are both bonding electrons. So, that is why it tends to fill first the bonding molecular orbital. So, these two are the molecular orbital, but this is the bonding molecular orbital or MO, and this is the anti-bonding molecular orbital. For bonding MO, it is denoted as sigma. For anti-bonding MO, denoted as sigma star. So, as discussed earlier, ang bonding MO has low energy compared to anti-bonding and is more stable or mao ang stable compared to anti-bonding. That is why the H2 molecule is a stable molecule compared to hydrogen element alone. So usually, di ba, atong kakakita is H2, dili H lang. So for helium or He2 molecule, naat kabaluta nga iyahang valence electron is 2. So for this is one helium element or atom and another helium atom. So iyaha nga na siya for the molecular orbital na feel niya ang bonding MO and the anti-bonding MO and na feel niya ang anti-bonding MO or the sigma star. So this is a unstable molecule. So that is why helium is a noble gas mong mas stable siya as He alone, dili He2. So for n equals to 2 nga molecular orbital, inani pod iyaha nga orbital. So naa dito ang 1s, then iha ang 2s, and then 2p. So these are the molecular orbitals, and this is for the atomic orbitals. So as the atomic number decreases, it becomes more likely that a 2s orbital on one atom can interact with 2p orbitals on the other. As the 2s-2p interaction increases, the sigma 2s molecular orbital lowers in energy and the sigma 2p orbital increases in energy. So for B2, boron, carbon, nitrogen, 2, the sigma 2p orbital is higher in energy than the pi 2p orbital. But for O2, F2, and Ne2, the sigma 2p orbital is lower in energy than pi 2p orbital. So, nakita ninyo diri, ang sa diri ang B2, C2, N2, higher iyahang sigma 2p compared to pi 2p. So, mas higher iyang 2p na orbital compared to pi 2p orbital. So for this is for molecular orbitals. So but for O2, F2 and Ne2, mas higher si pi 2p compared to sigma 2p. Okay, metallic bonding. Metallic bond is where the electrons are relatively free to move throughout the three-dimensional structure. So the physical properties of metals, they are luster, high electrical conductivity, high thermal or heat conductivity, malleability, and ductility. So electron C model for metallic bonding. In this model, the metal is pictured as an array of metal cations in a sea of electrons. Electrons are confined to the metal by electrostatic attractions to the cations, and they are uniformly distributed throughout the structure. In a metal, the number of atomic orbitals that interact or overlap is very large. Thus, the number of molecular orbitals is also very large. It is pictured to have energy band, dili na atomic orbital or molecular orbital, but energy band, having numerous and continuous tiny energy separation or between metal orbitals. Electrons available for metallic bonding do not completely fill the available molecular orbitals. Hence, it is partially filled and the electrons at the top require a little input to be promoted to still higher energy orbitals. Okay, so as you can see, for metallic bond, na nasa molecular bond or energy band na. According to the molecular orbital theory, metals are able to conduct electricity because there are molecular orbitals in the bond that are necessary to accommodate the bonding electrons. So in metals, an excited electron may easily move to a nearby higher orbital. Meanwhile, the bonding and the anti-bonding molecular orbitals of insulators such as diamond are separated by a large energy gap, so there are no nearby orbitals for the electrons to move to making diamond a poor conductor of electricity. So, that is why ang diamond dili siya ginagamit, though metal siya, dili siya or metallic siya, but dili siya ginagamit for electricity because it is a poor conductor. So that is all for the part 2, the bonding theories and molecular geometry of the unit 2 chemical bonding.